A ring the size of 2 basketball courts. Electrons circling it endlessly at nearly the speed of light. No lasers. No exploding metal droplets. That's what a team in China just built to replace the single most expensive component inside ASML's entire monopoly. Here's the number in this video's title that you need to hear first, because it's also the number I'm going to challenge before this video ends. $100 million. That's the reported price tag on this machine. Keep that number in your head, because in about 8 minutes, I'm going to show you exactly why it might not hold up. Here's what actually exists right now, not what a headline wants you to believe exists. Researchers at Tsinghua University have built a working test of something called steady-state microbunching, SSMB for short. Instead of firing a laser at tin droplets 50,000 times a second, the way ASML's machine does, SSMB accelerates a continuous stream of electrons around a storage ring, generating extreme ultraviolet light as a byproduct of that circular motion. No droplets to time. No plasma explosions to synchronize. Just electrons, circling, producing light that never stops flowing. Think about how different that actually is from everything ASML built its entire business on. ASML spent 3 decades perfecting a violent, precisely timed explosion, repeated 50,000 times every second, and turned that into the most profitable machine in the history of semiconductors. SSMB throws that entire premise out. No explosion. No droplet. Just a continuous, quiet stream of light, generated by physics that has nothing to do with vaporizing metal. This project isn't new either, and that timeline matters for what comes next. It's been running since 2017, led by Professor Tang Chuanxiang, building on theoretical work first proposed at Stanford back in 2010. 9 years of quiet development, only breaking into headlines recently because of the broader spotlight on Huawei's chip breakthroughs. 9 years. Not a rushed reaction to sanctions. A slow bet that's finally getting noticed. If a project timeline like that, quietly running for almost a decade before anyone outside China noticed, is the kind of detail you want more of, that's worth a comment below, because most coverage of this story completely skipped over how old this project actually is. Compare that timeline to how these stories usually get told. Most China catches up headlines make it sound like a project spun up overnight in response to export controls, a panicked scramble to work around a sudden ban. This one predates most of that pressure entirely. It was already years into development before ASML's tightest restrictions on China even existed, which makes it look a lot less like desperation and a lot more like a bet that happened to become strategically convenient once the pressure actually arrived. So why does this actually threaten ASML specifically, and not just annoy it? Here's the number that explains it. ASML's laser-based system loses roughly 98% of its own light before it ever reaches a wafer, bouncing off 11 separate mirrors on the way there, each reflection eating about 30% of what's left. By the time that beam does its job, it's down to less than 5 watts from a source that started around 250. 98% thrown away, every single exposure, by design. That's not a flaw ASML overlooked. It's the unavoidable price of being the only company that ever made this specific method work at all. Professor Pan Zhilong, part of the Tsinghua team, said publicly that SSMB has been designed with power higher than 1 kilowatt. 1 kilowatt against ASML's 250 watts. That's not catching up. That's a different category of output entirely, if it actually works at scale. But here's the part almost nobody explains, and it's exactly where that $100 million number starts to wobble. I could not independently verify that specific cost figure anywhere in the actual research reporting on this project. Not in the academic papers, not in the outlets covering the Xiong'an test site. It shows up in secondary coverage without a clear source attached. So before this video goes any further, that's worth saying plainly. The technology is real. The specific dollar figure attached to it right now might just be a number that sounded credible enough to repeat. Think about why a number like that spreads so easily, even without a source. $100 million sounds precise enough to feel researched, small enough to sound achievable, and big enough to sound serious. It hits exactly the sweet spot that makes an unsourced claim feel true on repetition alone. That's not proof it's wrong. It's just a reminder that a specific-sounding number isn't the same thing as a verified one. Keep that distinction in your pocket, because it's going to matter again in a minute. Here's something else almost no coverage of this story mentions, and it changes who you should actually be watching here. China isn't the only one chasing this exact idea. A company called X-Light in the United States is separately developing its own particle accelerator-based light source, using free electron lasers instead of SSMB specifically, but built on the same underlying premise: generate EUV without ASML's laser and tin droplet method. And here's the name that should genuinely surprise you. Reporting from just this week indicates Elon Musk is pursuing exactly this approach too, as part of a massive chip manufacturing project called Terafab, aimed at producing AI chips for SpaceX and Tesla at a scale approaching 70% of TSMC's entire current output. Musk isn't trying to buy more of ASML's machines. He's betting on skipping them entirely, using the same core physics China has been quietly developing since 2017. Sit with that for a second. This isn't a story about China racing to catch the West. It's a story about China and America racing each other toward the same escape hatch at almost the same time, using almost the same physics. Research-free electron lasers already exist, and they're genuinely massive, some stretching more than a kilometer long. The bet both sides are making is that this exact technology can be shrunk down small enough and made cheap enough to actually fit inside a real chip factory instead of a national physics lab. That shrinking problem is arguably harder than it sounds. A kilometer-long research instrument and a factory-floor production tool are separated by decades of engineering miniaturization work, the same kind of work that took ASML itself years to complete on its own laser system. Neither China's SSMB ring nor Musk's X-Light effort has published proof yet that this specific shrinking problem is solved, only that the underlying physics behaves the way the theory predicts. So is this actually a threat to ASML, or is this two separate research projects that happen to share an acronym-heavy premise? Let's not answer that with more hype. Let's answer it with a scorecard. What's real? The underlying physics. SSMB has been in development for 9 years, led by a real professor, with real published research behind it. X-Light and Musk's parallel effort in America prove this isn't a fringe idea invented for propaganda purposes. Real physics, developed independently on 2 continents, isn't something you can wave away as a single country's marketing exercise. What's unverified? The specific 1 kilowatt power figure, which comes from the research team's own design target, not an independently measured, sustained output from working hardware. And that $100 million price tag, which I could not trace back to a credible primary source anywhere. What's the actual bottleneck? Turning a kilowatt of raw light into something usable is a completely different problem than generating it. ASML's mirror system, expensive as it is, exists specifically to shape and focus light with atomic-level precision. SSMB still needs an equivalent optical system built around it, and nobody has published proof that peace exists yet at the power levels being promised. Generating raw power and taming it into something precise enough to print a chip are two entirely different engineering mountains. China's team has only climbed partway up the first one. What's the honest timeline? China's own internal targets, according to people close to related programs, point toward the early 2030s for anything resembling production-capable hardware from this specific approach. Independent analysts have been even more conservative. 4 questions. 4 honest answers. Real physics, wrapped in a specific number that doesn't hold up under scrutiny. Now here's where this story shifts, because up to this point, everything's been about the light source itself. There's a bigger question sitting behind it. If both China and the United States are independently racing toward the same laser-free alternative to ASML's monopoly, what actually happens to ASML if either one succeeds? Here's the uncomfortable answer for ASML shareholders. It doesn't matter which country gets there first. A working, commercially viable particle accelerator light source breaks the specific choke point ASML has owned for 2 decades, regardless of whose flag is on the building. Export controls were built around the assumption that only ASML's specific laser and mirror method could generate this wavelength of light reliably. That assumption is being tested from 2 completely different directions at once right now. Think about what that actually means for the export control strategy the United States has leaned on for years. That strategy was never really about stopping China specifically from owning a laser. It was about controlling the only known method of generating this wavelength of light at industrial scale. If a second method exists and works, the entire logic of that choke point stops applying, no matter who built the alternative or which government approved funding it. But there's one place where China and America's approaches actually diverge in a way that matters. X-Light is explicitly designing its light source to feed into ASML's own existing scanners, working with the current system rather than replacing it outright. China's SSMB approach is aimed at bypassing ASML's entire architecture, mirrors and all, building something meant to stand completely independent of it. One path cooperates with the incumbent. The other tries to make the incumbent's core product obsolete. Those are very different bets, even though they start from the same underlying physics. It's worth noticing what that difference actually says about each country's relationship to ASML, too. X-Light's approach assumes ASML stays relevant, just with a better engine installed under the hood. China's approach assumes ASML's entire architecture becomes optional the moment a viable alternative exists. One is a partnership pitch. The other is a eulogy, written a decade early. Here's why this specific technology matters more than just being a curiosity for physicists, too. Every AI chip, every advanced processor, every piece of hardware training the models people use every day eventually depends on this exact wavelength of light getting generated reliably, at scale, by somebody. Right now, that somebody is one company in the Netherlands. A second, third, or fourth viable method of generating that light doesn't just threaten a stock price. It threatens the entire structure of how the global chip industry has organized itself around a single point of failure for over 2 decades. Think about what a world with 3 separate viable EUV generation methods would actually look like, instead of just one. Prices could shift. Supply chains could diversify. Countries currently locked out of advanced chip making because they can't buy an ASML machine might suddenly have other doors to walk through. That's the actual stake sitting behind a ring built to hold circling electrons in a facility outside Beijing. There's also a talent dimension to this race worth watching closely. Both the Tsinghua effort and X-Light draw on decades of accumulated particle physics expertise, the kind of knowledge base that exists at only a small number of universities and national labs worldwide. Whichever program manages to attract and retain more of that specific talent pool over the next 5 years likely determines which approach actually reaches a factory floor first, regardless of which country currently claims to be ahead on paper. Watch the optics problem specifically over the next year or two, since every credible analyst covering this story agrees that's the real remaining wall, not the light source itself. Watch whether Musk's Terafab timeline holds up, since a public figure with his track record of ambitious deadlines gives outside observers an unusually visible benchmark to measure progress against. And watch whether China's own state media starts attaching more specific, sourced cost figures to this project. Because right now, the fuzziness around exactly what this costs is itself a signal about how early stage this technology actually still is. So let's recap where this actually leaves us, because a lot just happened. China built a real 9-year-old particle accelerator project targeting more than 4 times ASML's current power output. The specific $100 million price tag in this video's title doesn't trace back to a verifiable source. America is chasing a parallel version of the same idea, publicly, through Musk's own chip ambitions. And the actual bottleneck isn't generating the light anymore. It's building an optical system precise enough to actually use it. Ring built. Physics proven. Price tag unverified. Optics unsolved. 2 countries, 1 finish line. Here's the verdict. This is not a $100 million nightmare machine that already replaced ASML's lasers. It's a genuinely serious 9-year physics program that's proven the core concept works, sitting years away from proving it can be built into something a real chip factory could actually run. Real breakthrough. Overstated headline. Both true about the same project. There's a broader lesson in that split, one that applies well past this single machine. The most useful habit you can build watching stories like this one isn't picking a side, hype, or dismissal. It's asking which specific number in the headline actually traces back to a source, and which one just sounded precise enough to survive being repeated. That habit will serve you on every single one of these stories going forward, not just this one. Which side of this race do you think actually gets there first? China's SSMB approach, or Musk's X-Light effort? Drop your pick in the comments, because I'm tracking both of these in parallel. And whoever's right is going to look very smart in about 3 years. Whichever one wins doesn't just change a chip factory. It changes who controls one of the most important choke points in the entire global economy. And right now, that answer is genuinely still up for grabs. The next video breaks down exactly what's standing between a working light source like this one and an actual chip you could hold in your hand, and why that gap has quietly become the hardest problem in the entire industry.